Now, when it comes to integration, there are some functions that are just too hard to integrate. And in fact, there's some functions you just can't. Right? We just don't have the techniques to do it. So we need ways to approximate and come up with it. And the way we're going to look at it is this thing called the trapezoidal rule. We started off by estimating with rectangles and we got a massive overestimate or an underestimate, depending on which way we took it. Well, if instead of doing a rectangle, we did a trapezium, then straight away we're going to cut out that overestimate, because we're now going to have a diagonal joining those two function values, and you can see that the overestimate is a lot less than it would have been if we had a rectangle. So if the curve's concave up like this one, we'll end up with an overestimate, but if it was concave down, we'd end up with an underestimate, because the diagonal would come underneath the curve. So we can approximate it with the formula for a trapezium. So recall that the formula for a trapezium, half the height, well in this case the height is the difference between B and A. So B minus A on 2 times the sum of the y values, or the function values, so function A plus function B. But just like we saw with rectangles, the more trapeziums that we have, the better the estimate. So what would happen if I just did 2 trapeziums? So again, our overestimate has been cut down. So we'd have the sum of these 2 trapeziums, but if we place C in a sensible spot, in other words, in the middle, then C minus A and B minus C is going to be the same value. So I can factorise this. And I've factorised it to be C minus A on 2, but it doesn't really matter, because as I say, C minus A, B minus C, same thing. But we'd end up we'd still have function A and function B, but we're now going to have twice function C, because it's in both of the trapeziums. Well, let's break it into 3. Again, you can see our overestimate is now getting very small. We have 3 trapeziums add together, but again, if we choose C and D sensibly, so that C minus A is the same as D minus C is the same as B minus D, we can factorise out, I wrote it as C minus A on 2, but we will also have one of the function values at the end, but then each of the ones in the middle are involved in 2 trapeziums. So we'll get twice those values. And that pattern will keep happening. So for want of a better formula, this is the way I write it. So we know the exact area will be the integral. But okay, we can't integrate the function, it's too difficult, whatever. We can approximate it with this. So I write it this way. H on 2, so the height of the trapezium, whichever one I pick, B minus D, D minus C, C minus, whichever one. But then I say y0 plus yn. They're my 2 end ones. So I actually call the first one y0 rather than y1. I'll explain why in a sec. But then I just go, and 2y, the other ones. So all the ones in the middle. So I just say, 2y, the others. So that's my formula. So why do I make it yn at the end? Well, that's because n is the number of trapeziums I'm splitting it into. So you're always going to have one more function value than you are trapeziums. So I like to finish off with n for being the last one. The height then will be b minus a, so the 2 endpoints, divided by the number of trapeziums, because you're splitting into that many trapeziums. Oh, that's what I say. So there's always one more function value than we do have intervals. So sometimes you'll see them called trapeziums, sometimes they'll say intervals, sometimes they'll say sub-intervals, sometimes they'll say strips. But all these terms were just pieces of the area. So let's do it with this one. And I've picked a shape that at this stage we don't know how to integrate. We'll work out how later. But we can find the exact value of. So I've picked the semicircle, the square root of 4 minus x squared, and we're going between 0 and 2. So basically it's a quarter of a circle is what we're finding here. Well, we want 4 intervals. So the height of each one, the endpoints, 2 minus 0, divided by the number of intervals, number of trapeziums, whatever. So 0.5. That's how big they're going to be. So I then draw up a table of values. And I know I'm going every 0.5. I need those function values. So then I work out those function values. They've said to 3 decimal places, so I always carry 1 extra decimal place in my calculations, and then I'll round off to 3 decimal places at the end, just to avoid any rounding errors that might happen if I round too early. Okay, there's my formula. H on 2, y0, yn, 2y, all the other ones. But just to remind myself, what I like to do is, on my table of values, I go, okay, yeah, that's right. It's 1 times the end ones, and then 2 times all these middle ones. So it just reminds me, that's what I'm multiplying by. So subbing in, 0.5 on 2, 2 plus 2, all the middle ones, and so on, and we get 2.996 to 3 decimal places. Well, the exact value I say we can work out, I picked the numbers nicely, so it just turns out to be pi, because it's a quarter of pi r squared. The radius in this one was 2, quarter of 4 pi is pi, which is of course 3.14, etc., etc. So how good was it? Well, the difference there, percentage difference, is 4.6%. So that's how much error I got for this one. There is another way of setting this out, which is quite neat. Okay, there's my table of values. I wrote it out like that. There's your trapezoidal rule. So essentially what it is there's what was in the middle. The y naught, the yn, 2 times the others are in the top of the fraction. But on the bottom, you just add all of these numbers that I wrote on the top here. So 1 plus 2 plus 2 plus 2 plus 1. But then you multiply it by the height of the trapezium. So in this case, 2 minus 0. And amazingly, it comes out to be the same thing. It's just a different way of setting it out if you prefer. Okay, so how have they asked these sort of questions in the past? So 2020 was the first of the current course. It was question 20 in the 2-unit paper. Kenzo. Kenzo? Who's called Kenzo? Kenzo's driving his car along a road while his friend records the velocity of the car in kilometres per hour. And there's their table of values. Then they tell us, well, the distance covered would be the integral of this velocity function, and it's a 5-minute period, so there'll be 0 to 5/60ths. Okay. But then they told us to use the trapezoidal rule because we don't know what the function is in this case. So it would be impossible to integrate it. So use the trapezoidal rule, velocity at each of those 6 values to approximate the distance in kilometres the car has travelled, correct to 1 decimal place. So there's our table of values. There's my formula. That's right, it's 1 times the m1, 2 times all the ones in the middle. Height on 2, bingo, 5.4 kilometres is what that one comes out to be. There's the alternative working out. If I'd done it the other way, that's what it would have looked at. So on the bottom of the fraction, we get the 1 plus 2 plus 2 plus 2 plus 2 plus 1, then times the width of the trapezium, or the height of the trapezium, 5/60ths minus 0, and again, amazingly, 5.4 kilometres. Okay, that's our trapezoidal rule.